Welcome to the deep dive. Today, we're doing something a little different. We're
Oh,
not just diving deep, we're launching into a kind of high-energy interactive challenge.
sounds fun.
Get ready, because it's a quiz show deep dive, designed to really sharpen your understanding of the very stuff that makes up, well, everything.
Ah, I see where you're going with this. Matter.
Exactly. Our mission today is to tackle some truly foundational questions about matter. The building blocks of our universe.
And turn them into those satisfying aha moments.
Precisely. We're going to challenge your knowledge with some multiple choice questions, and then we'll unpack the answers together.
Digging into why they're correct and what surprising insights they reveal about the world around us.
Think of it as a fun, maybe a fast-paced shortcut to being incredibly well-informed, ensuring you truly grasp these concepts.
And this isn't just an academic exercise, right?
Not at all.
Understanding these fundamental concepts about matter truly helps us make sense of everything we interact with daily. Well, from the air we breathe and the food we eat to the technology in our hands.
Right.
This deep dive will challenge some of your assumptions, I think, solidify your foundational knowledge.
And maybe even change how you look at the world.
Hopefully, all while keeping things engaging and, well, enjoyable.
Okay, let's dive into the first question then. Ready?
Let's do it.
Okay, think about everything you see, feel, maybe even can't see: the air, food, stones, clouds, stars, plants, animals.
Even just a single drop of water.
Right. What do scientists call the fundamental material that all of this is made up of? Your options are A, energy,
Okay.
B, space, C, matter, or D, volume. What do you think?
Well, if you chose C, you're on the right track. The answer is matter.
Matter. Seems basic, but it's huge.
It is. This isn't just a basic definition. It's the foundational concept for understanding the entire universe.
Yeah.
Matter is the unifying stuff that has both mass and occupies space.
So quite literally, everything.
Pretty much. And grasping this simple concept, it just opens doors to countless scientific marvels.
It's incredible to think how something so fundamental could have been viewed so differently across time, though.
Absolutely. Ancient views were quite different.
Yeah, that brings us to a fascinating historical detour. Ancient civilizations, they had their own profound ideas about matter long before modern science.
Hmm.
So, according to early Indian philosophers, what were the five basic elements? The Panchtattva, literally. Five essences that made up all matter, living and non-living.
Okay, what are the options?
Your options: A, water, air, earth, fire, metal. B, air, earth, fire, sky, water. C, wood, metal, water, fire, earth. Or D, air, land, sea, sky, sun.
Okay, thinking about those early philosophies,
Mhm.
the answer is B, air, earth, fire, sky, water.
Sky, interesting.
Yes, it highlights the different historical approaches, doesn't it?
Mm.
It wasn't always about tiny particles and chemical bonds back then.
Right.
Earlier philosophies sought to understand the world through more observable, macroscopic elements. They were trying to explain the world with the tools they had.
Makes sense. Okay, fast forward to today. Our understanding has evolved significantly.
Massively.
Modern scientists have developed two primary types of classification for matter. These classifications are based on what fundamental characteristics?
All right, lay them on me.
Your options are A, shape and size,
Mm.
B, physical properties and chemical nature, C, mass and volume, or D, color and texture.
This one really gets to the heart of modern chemistry. The answer is B, physical properties and chemical nature.
Physical properties and chemical nature.
Exactly. This shift really shows the evolution of scientific thought, from that ancient philosophy to detailed empirical observation,
So we move from broad elements.
to understanding the intrinsic characteristics and behaviors of substances, how they react, what they do. It allows for a much more nuanced and predictive science.
Okay, here's where it gets really interesting, I think. We're going to dive into the idea that matter isn't just one continuous blob.
The particulate nature.
Exactly, but it's made up of tiny, discrete particles. Imagine you're dissolving salt or sugar in water.
Okay, got it.
You watch it disappear, right, but the water level doesn't really change much.
Right, maybe a tiny bit, but not what you'd expect if it were continuous.
So which of these observations best supports the idea that matter is made of particles with spaces between them? Options: A, lighting an incense stick.
Smell diffusion.
B, dropping copper sulfate into hot and cold water. C, dissolving salt sugar in water and observing no significant change in water level. Or D, trying to break an iron nail.
Okay, thinking about those spaces, the best fit is C. dissolving salt, sugar, and water, and observing no significant change in water level.
Why that one specifically?
Well, it raises that key question.
Yeah.
If matter were truly continuous, like a solid block, where would the salt or sugar go when it dissolves?
It would have to push the water level up, right?
Exactly. The fact that the water level doesn't significantly change tells us there must be tiny spaces between the water particles.
Ah, for the salt or sugar particles to slot into.
Precisely. It's direct evidence of that particulate nature, a really foundational concept.
That's a brilliant way to visualize it. Makes you realize even seemingly solid stuff is full of invisible gaps. Okay, building on that, think about this. If you take a tiny crystal of something really colorful, say potassium permanganate.
That purple stuff.
Yeah, and you dissolve it in water, then take some of that water and dilute it again and again and again.
Heat diluting.
You'd still see a faint color even after many, many dilutions. What does that surprising persistence primarily demonstrate about matter's particles?
Okay, the fact that the color hangs around.
Your options. A, particles of matter have space between them. B, particles of matter are continuously moving. C, particles of matter are very small. Or D, particles of matter attract each other.
This one points to just how incredibly numerous these particles are. The answer is C. Particles of matter are very small.
Very small. How does the color prove that?
Because the persistence of color, even after it's spread through so much water, is astonishing. It means just one single tiny crystal must contain millions upon millions of incredibly tiny particles.
Wow.
Each one carrying that color, even though they're individually invisible. It really boggles the mind how small we're talking.
So, okay, particles are tiny. They have spaces between them. What else?
They're not just sitting still.
Right. So back to the sugar and water example. The particles spread throughout the water. Level doesn't change. This again illustrates that. A, matter is continuous. B, particles of matter have space between them. C, particles of matter are very small. Or D, particles of matter attract each other. Which aspect does this dissolving highlight?
We circle back to it, but it's such a good illustration of B. Particles of matter have space between them.
Just reinforces that idea of the gaps.
It really does. How else could they mix so thoroughly without increasing the volume noticeably? Those interstitial spaces are key.
Okay, speaking of movement then, what happens to the energy of motion of these particles as the temperature rises? This is a classic.
Absolutely fundamental.
Your options. A, it decreases. B, it remains constant. C, it increases.
Never.
It first decreases, then increases.
No doubt about this one. The answer is clearly C. It increases.
More heat, more jiggle.
You got it. The direct relationship here is crucial. More heat energy means more kinetic energy, which translates directly to faster moving particles.
So that increased kinetic energy is what we actually feel as temperature.
Exactly. It's why things feel hotter. The particles are literally vibrating and moving more vigorously at the microscopic level.
That movement leads us to something called diffusion. Remember the incense stick option earlier?
Ah, yes, the smell spreading out.
Right. So the intermixing of particles of two different types of matter on their own, just by getting into the spaces between the particles. What's that called? Options A, evaporation. B, condensation. C, sublimation. Or D, diffusion.
That specific process of mixing is D, diffusion.
Diffusion, got it.
It's the natural tendency of particles, because they're moving, to spread out and occupy all the available space, moving from where there's lots of them to where there's fewer.
High concentration to low concentration makes perfect sense. And sticking with heat, how does heating generally affect the rate of diffusion? How fast it happens?
Good follow-up.
Options. A, heating slows down diffusion. B, heating stops diffusion. C, heating makes diffusion faster. Or D, heating has no effect on diffusion.
Think about smells again. The answer is C. Heating makes diffusion faster.
Like hot food smelling stronger.
Exactly. Think about the difference between the subtle scent of cold leftovers versus the amazing aroma that fills your kitchen when you're reheating something delicious.
Or fresh coffee brewing.
Perfect example.
Yeah.
It's all because those particles get that kinetic energy boost from the heat. They just zoom around faster, intermixing much more rapidly.
Okay, we've covered tiny particles, spaces between them, and constant movement. But there's one more crucial characteristic, isn't there?
There is indeed. The glue.
The glue, okay, imagine trying to form human chains, holding hands tightly, then maybe trying to break an iron nail.
Which is tough.
Or even just trying to cut the surface of water with your fingers. You can feel something resisting.
A little bit, yeah.
These actions, based on your own experience, collectively suggest which characteristic of particles. Options. A, particles are very small. B, particles are continuously moving. C, particles have space between them. Or D, particles of matter attract each other.
The key here is the resistance, the holding together.
Hmm.
The answer is D. Particles of matter attract each other.
So there are forces pulling them together.
Exactly. It's this unseen attraction that really dictates how matter behaves. The ease or difficulty of breaking something or pulling it apart tells us directly about the strength of those forces.
So it's not just that they attract, but the strength of that attraction is what makes a solid solid and a gas a gas.
Precisely. You've hit the nail on the head. The strength of these attractive forces varies dramatically between different substances and different states.
Okay.
That's exactly why solids are so rigid, strong forces. Liquids flow because the forces are weaker, allowing movement. And gases spread out easily because the forces are almost negligible.
It's a whole spectrum of stickiness.
Kind of. It's all about how strongly those particles hold on to each other.
Okay, let's pivot then to those three main states of matter: solids, liquids, and gases. First up, solids.
Right.
They're characterized by maintaining their shape, being difficult to change.
Wow.
This property is known as what? A, fluidity, B, compressibility,
Oh.
rigidity, or D, diffusivity.
That property is C, rigidity.
Rigidity. Makes sense.
Solids have those tightly packed particles we mentioned, with really strong forces of attraction between them. That essentially locks them into fixed positions, giving solids their definite shape and making them resistant to bending or breaking.
Okay, what about liquids then? Which statement accurately describes their properties? Options: A, fixed shape and fixed volume. B, no fixed shape but fixed volume. C, fixed shape but no fixed volume. Or D, no fixed shape and no fixed volume.
For liquids, the correct description is B, no fixed shape but fixed volume.
So they flow, but the amount stays the same.
Exactly. Unlike solids, liquid particles have enough energy to slip and slide over each other. That's why liquids take the shape of their container.
Like pouring water from a bottle into a glass.
Perfect example.
Oh,
It conforms to the glass shape, but the total amount of water, the volume, stays the same.
got it. And then gases. They're known for being highly compressible.
Very compressible.
An everyday application of this property is seen in what? Options: A,
Uh-oh.
water flowing easily.
Mm.
B, the smell of hot food reaching you.
Mm.
C, liquefied petroleum gas, LPG, and compressed natural gas, CNG, stored in cylinders. Or D, sugar crystals keeping their shape.
The obvious example here is C, LPG and CNG stored in cylinders.
Like for BBQs or natural gas vehicles.
Exactly, these are familiar examples of taking gases. LPG is liquefied petroleum gas, CNG is compressed natural gas, and squeezing them into much smaller, more manageable volumes.
And that works because
Because of the huge spaces between gas particles, it allows them to be forced much closer together under pressure.
right. Now, why does a gas exert pressure on the walls of its container, like air in a balloon?
Ah, the pressure question.
Options: A, due to strong forces of attraction between gas particles.
Yeah.
B, because gas particles move about randomly at high speed and hit the walls of the container. C, because gas particles are fixed in position. Or D, due to the negligible kinetic energy of gas particles.
The pressure comes from movement. It's B. Because gas particles move about randomly at high speed and hit the walls of the container.
So it's like a constant bombardment.
Exactly that. Billions upon billions of tiny particles constantly moving, constantly colliding with the container walls. Each tiny collision exerts a tiny force, and all those forces added up create the pressure we measure.
Okay, let's do a quick summary of the states of matter. A few rapid-fire checks for you listening.
Test your recall.
In which state are the forces of attraction between particles considered to be maximum? Take a second.
If you thought solids, you're absolutely right. Those strong forces lock everything in place.
Good. Now, where do we find the greatest spaces between particles and the highest kinetic energy? Think about it.
That would definitely be gases. All that freedom, all that movement, lots of empty space.
Perfect. And finally, how would you describe the arrangement of particles in the gaseous state? Any order.
Nope. The answer is no order. Particles just move about randomly. It's pure, beautiful, microscopic chaos.
So this quick recap really highlights the key differences, doesn't it?
Absolutely. Solids, ordered, tightly bound. Liquids, close, but fluid.
Yeah.
Gases, far apart, chaotic movement. These distinct arrangements dictate all their physical properties.
Okay, let's move on to how matter actually changes states. Phase transitions.
The exciting part, melting, boiling.
Exactly. First question. What is the minimum temperature at which a solid melts to become a liquid at atmospheric pressure called? Options: A, boiling point. B, freezing point. C, melting point. Or D, sublimation point.
That specific temperature threshold is C, melting point.
Melting point, where it starts to loosen up.
Right, where the particles gain just enough energy to start breaking free from those fixed positions in the solid structure and transition into a more fluid state.
Now, here's a tricky bit. When a solid melts, say ice turning to water, its temperature stays constant at the melting point, even if you keep heating it.
Ah, the plateau on the heating curve.
Right. This absorbed heat energy, the energy used just to overcome the forces and change the state, not raise the temperature, what's that called? Options. A, kinetic energy. B, specific heat. C, latent heat of fusion. Or D, thermal capacity.
That hidden heat is C, latent heat of fusion.
Latent, meaning hidden. Why is that so important?
It's crucial. This latent heat explains why, for example, ice is so effective at cooling a drink. It absorbs a lot of heat without getting warmer itself, just to make the phase change.
So the energy is busy breaking bonds, not just making particles jiggle faster.
Precisely. It's energy doing the heavy lifting of transformation, dismantling the solid structure, before the temperature can rise further.
Okay, similarly then, what is the temperature at which a liquid starts boiling at atmospheric pressure? Options. A, melting point. B, freezing point. C, boiling point. Or D, condensation point.
That would be C. Boiling point.
Boiling point, where it turns into gas.
Yes, specifically, it's the temperature where the liquid's vapor pressure equals the surrounding atmospheric pressure. That allows bubbles of vapor to form throughout the bulk of the liquid, not just at the surface.
This is a whole liquid event.
A full-body transformation, you could say.
Now think about steam versus water. Particles in steam at 100 degrees C, or 373 K, actually have more energy than liquid water at the exact same temperature. Why is that?
Seems counterintuitive. Same temperature, but more energy.
Options. A, steam particles move slower. B, steam particles have absorbed extra energy in the form of latent heat of vaporization. C, water particles have lost energy. Or D, water has a higher density than steam.
It's that latent heat again. The answer is B. Steam particles have absorbed extra energy in the form of latent heat of vaporization.
Another dose of hidden energy.
Exactly. Just like melting requires latent heat of fusion, boiling requires latent heat of vaporization. This extra energy is needed to completely break the remaining intermolecular forces and let the particles escape as a gas.
And that's why steam burns can be worse than hot water burns?
Precisely. That extra stored latent heat gets released onto your skin when the steam condenses, delivering a bigger thermal punch even at the same temperature.
Ouch. Okay, now for a more dramatic change. The direct change of state from solid straight to gas, skipping the liquid phase entirely. What's that called?
The disappearing act.
Options. A, evaporation. B, condensation. C, sublimation. Or D, deposition.
That direct solid to gas jump is C, sublimation.
Sublimation. And a classic example is?
Solid carbon dioxide, better known as dry ice.
Right. So knowing what sublimation is, why is it called dry ice? Options. A, it melts at room temperature. B, it gets converted directly into the gaseous state on decrease of pressure without coming into the liquid state. C, it's a solid with very low density. Or D, it can be easily compressed into a liquid.
The dry part comes from skipping the liquid phase. So it's B. It gets converted directly into the gaseous state without coming into the liquid state.
At normal atmospheric pressure, anyway.
Correct. This raises that important point again. It's not just temperature. Pressure plays a huge role, too. Dry ice at the pressure we live in never becomes a puddle. It just vanishes into CO2 gas.
Exactly. Which leads perfectly to the next point. How can applying pressure affect the state of matter, especially for gases?
Pressure's effect.
Options. A, increasing pressure causes gases to expand. Definitely not that one. B, applying pressure and reducing temperature can liquefy gases. C, decreasing pressure converts gases to solids directly. Or D, pressure primarily affects the shape, not the state.
We touched on this with LPG and CNG. The answer is B. Applying pressure and reducing temperature can liquefy gases.
The combo punch.
Right. Squeezing those gas particles closer together with pressure and slowing them down by reducing the temperature forces them into the liquid state. That's how we store those gases efficiently.
Okay, so to tie this whole section on changing states together, the states of matter are interconvertible. We can change them. The state can be changed by altering which two fundamental physical conditions?
The two main control knobs.
Options. A, size and shape. B, mass and volume. C, temperature and pressure.
Right.
Or D, color and texture.
It's got to be C. Temperature and pressure.
Temperature and pressure.
Those are the two fundamental levers we pull, the main ways we influence the energy and proximity of particles to drive those fascinating phase transitions we've just discussed. They are the twin architects of state change.
Great summary. Okay, let's zoom in on one specific phenomenon we see all the time, evaporation.
Ah, the puddle drying up.
Exactly. What is the phenomenon where a liquid changes into vapors at any temperature below its boiling point?
Well-
Options: A, boiling, B, melting C, evaporation, or D, condensation,
That everyday process is C,
evaporation.
evaporation. And what's fascinating here, as you hinted, is how different it is from boiling. Boiling needs that specific temperature, the boiling point. But evaporation, it can happen anytime, even from cold water.
Indeed. So let's clarify that difference. Which statement best distinguishes boiling from evaporation? This is a bit longer.
Okay, focus.
Options: A, boiling is surface, evaporation is bulk. B, boiling is any temp, evaporation is only boiling point. C, boiling is a bulk phenomenon, particles from the entire liquid change state, whereas evaporation is a surface phenomenon, only particles from the surface gain enough energy to escape. Or D, boiling causes cooling, evaporation causes heating.
Okay, thinking about how they happen. The key difference is described in C. Boiling is a bulk phenomenon. Evaporation is a surface phenomenon.
Bulk versus surface. Explain that a bit more.
Well, boiling, you see bubbles forming throughout the liquid. It's vigorous, happening everywhere inside at once.
Yeah.
Evaporation, on the other hand, is just the particles at the very top layer, the surface, having enough energy to break free and drift away as vapor.
So boiling is more dramatic, evaporation is more subtle.
Exactly. Boiling is an all-hands-on-deck transformation you can clearly see, while evaporation is a quieter, constant escape from the liquid surface, often invisible unless it's happening rapidly.
Makes sense. Now, what factors can increase the rate of evaporation, make it happen faster?
Things that help those surface particles escape.
Options: A, a decrease in surface area, B, a decrease in temperature, an increase in humidity, or D, an increase in wind speed.
More wind helps. The answer is D, an increase in wind speed.
Why does wind speed it up?
Wind literally blows away the water vapor molecules that have just evaporated and are hovering right above the surface. This lowers the concentration of vapor in the air right there, making it easier for more liquid particles to escape.
Clears the runway, so to speak.
Pretty much. And of course, other factors matter too. Increasing surface area gives more runway. Increasing temperature gives particles more energy to escape. Decreasing humidity means the air is less saturated and can hold more vapor.
Right. This leads us to a really crucial consequence of evaporation. Cooling. We feel it all the time.
Like getting out of a pool on a breezy day. Brr.
Exactly. How does evaporation actually cause cooling? Options: A, liquid particles release energy. B, the particles of liquid absorb energy from the surroundings to regain energy lost during evaporation, making the surroundings cold. C, evaporation generates heat. Or D, the volume increases, causing coolness.
The cooling effect comes from energy absorption. It's B. The particles of liquid absorb energy from the surroundings, making the surroundings cold.
So the escaping particles take energy with them.
Precisely. It's the most energetic particles, the fastest moving ones at the surface, that have enough oomph to break free and evaporate. When they leave, they take that kinetic energy with them.
Leaving the slower, cooler ones behind.
Exactly. And to replace the energy lost by those escaping particles, the remaining liquid and its immediate surroundings contribute heat. That transfer of heat away from the surroundings is what causes the cooling effect.
That's why sweating cools us down.
Perfect biological example of evaporative cooling.
Okay, connecting that idea. After a hot, sunny day, people sometimes sprinkle water on the roof or open ground. This helps cool the hot surface primarily because of what property of water?
Using evaporation for cooling.
Options: A, water's low density. B, water's ability to reflect sunlight. C, the large latent heat of vaporization of water. Or D, water's high surface tension.
It connects directly back to that latent heat we discussed. The answer is C. The large latent heat of vaporization of water.
Explain that connection.
Water requires a surprisingly large amount of energy just to change from liquid to vapor. That's its high latent heat of vaporization. So when that sprinkled water evaporates from the hot roof, it has to absorb a substantial amount of heat energy from the roof surface to make that phase change.
Pulling the heat out of the roof.
Exactly, effectively cooling it down. It's like a natural low-tech air conditioner.
Yeah.
Very effective.
Neat. Okay, final question for this segment. Why do we see water droplets forming on the outer surface of a glass containing ice-cold water? That condensation.
The sweaty glass effect.
Options: A, the cold glass attracts water from inside the air. B, water leaks through pores in the glass. C. The water vapor present in the air loses energy on contact with the cold glass and condenses into liquid droplets. Or D. The cold glass causes the air to solidify.
It's all about the water vapor already in the air. The answer is C. The water vapor present in the air loses energy upon contact with the cold glass and condenses.
So it's the reverse of evaporation.
Exactly. Condensation. The cold glass surface cools the air immediately around it. The invisible water vapor molecules in that cooled air lose kinetic energy. They slow down.
And slow down enough
To clump together and turn back into visible liquid water droplets on the cold surface. It's the water from the air, not from inside the glass.
Got it. Okay, just a couple more quick questions to round out our deep dive quiz. Temperature units.
Important for science.
What is the SI unit of temperature the standard scientists use worldwide? Options. A. Celsius, degrees C, Fahrenheit, degrees after C, Kelvin, K or D, Joule J.
The standard international unit is C, Kelvin, K.
Kelvin. Why Kelvin and not Celsius, which we use more often day to day?
Well, the Kelvin scale is incredibly important in scientific calculations because it's an absolute temperature scale.
Absolutely.
Meaning 0K represents absolute zero. That's the theoretical point where particles have the minimum possible kinetic energy, essentially no movement. Celsius has its 0 point at freezing water, which is arbitrary from a fundamental energy perspective. Kelvin starts at the real bottom.
Okay. It's the true baseline for energy.
Exactly. Crucial for many scientific laws and formulas.
Okay, last question then. To make sure you can handle conversions if you see Kelvin used, how do we convert a temperature from the Kelvin scale to the Celsius scale? Options A, add 273, top it out, B, subtract 273, C, multiply by 273, or D, divide by 273, approximately 273, technically 273.15, but 273 is usually fine.
To go from Kelvin to Celsius, you need to shift that 0 point. So it's B, subtract 273 from the given temperature.
Subtract 273.
Yeah, so 273K minus 273 gives you 0 degrees C, the freezing point of water. 373K minus 273 gives you 100 degrees C, the boiling point. It's a simple shift, but vital for comparing and using temperatures accurately in science.
Wow, what a journey. That was quite the quiz deep dive.
It covered a lot of ground.
From the fundamental definition of matter, its ancient roots, right through to its particulate nature, the dynamic dance of those particles.
The three main states, how they change with temperature and pressure.
And that fascinating process of evaporation and cooling, plus temperature scales. You listening just navigated a full-on quiz, and I really hope you had as much fun learning as we did exploring these ideas with you.
It's been incredibly insightful, hasn't it?
Yeah.
We've really unpacked everything from those early philosophical views right up to the modern scientific understanding that, well, underpins our entire world.
It really does.
So here's a final thought for you to ponder. The next time you see steam rising from, say, a hot cup of tea, or you feel that cool breeze on your skin after exercising, what new questions might you ask about that invisible dance of particles that makes it all possible? Think about it. Every sip of water you take, every breath of air, every solid object around you, it's all a testament to these fundamental principles of matter.
Constantly in motion, constantly transforming.
Exactly. Always interacting according to these rules we've explored.
Absolutely. Keep exploring, keep observing the world around you, and definitely keep asking those questions with this newfound understanding. Your world just got a whole lot more interesting, microscopically speaking.
Hopefully.
Until next time, keep diving deep.